Okay, so your quiz tomorrow. Your quiz tomorrow is going to be largely based off of this worksheet. Okay, because this is everything we've been talking about: states of matter, particle movement, spacing, even a little mention of density. Okay, so your quiz is going to be based off this worksheet, this, and one other thing. The one other thing was the thermometer modeling, which I will also go over that in this video. But really, that's the same thing as what we're explaining on this worksheet. It starts off by talking about some learning objectives. It gives you a model here showing a gas, a liquid, and solid. And it's not exactly like how we do our models, but still gives you a good idea. So like gases are spread out, they're moving fast. Liquids are a little closer together, moving a little slower. And solids are very, very close together. And they're not even moving around, they're just kind of jiggling back and forth. So we're going to answer our questions here that we have, key questions, the table. So spacing and relative density. So solids are close together. And the more compact particles are, the closer together the particles are, the more dense they are. So this is most dense phase. And it makes sense because we think of density in objects floating in one another, different substances. Usually we can think of solids sinking in liquids, right? Usually that's the case, not always, but usually. Liquids spread apart, not crazy spread apart, but they're spread apart. We'll call those middle dense or middle density. Or you could say less dense than solids. Gases, most spread apart. And since they are most spread apart, they are least dense. All right. Movement and relative kinetic energy. Remember that the kinetic energy is basically like the speed, okay? So movement of a solid, it stays in place. The particles stay in place. And so it's got low kinetic energy because the particles aren't moving very fast. Liquids movement, move, I should say, way they commonly phrase it, slide past each other. And this will be the middle kinetic energy, so they're moving a little faster than solids, slide past each other. Gases go everywhere, and they're moving the fastest, so they have the highest kinetic energy, okay? Filling a container. So if we put these types of phases in a container, will they fill the container? Will they take the shape of the container? All right, so a solid will not just magically expand and take up the same space of its container. So filling a container volume, I'm just going to say no there. No, it doesn't. And a liquid, if I pour a liquid in a container, it's not going to like expand and always take the same size of the container either. If we fill a container, then yes, but what this is saying is if we just put a sample of the substance in there, is it going to take the same size of the container, the volume? So that's a no on liquid as well. Now gases, since they go everywhere available, if I put gas into a container, the gas particles will spread out and cover the entire space available, which means the same volume. So that's a yes. The shape, so solids do not take the shape of their container. Liquids do, however, and so do gases. All right? So on that last column, I was saying just doing shape. Okay, so moving on from here. Oh no, this isn't going to work. I'm going to do this on the notebook page. All right, so question number 2. In which phase of matter is there the least spacing of particles? So 2, least spacing of particles would be a solid. Number 3, in which phase of matter is there the most potential for movement? That's also going to be solid, because if it has the least movement, that means it has the most potential to have movement. I'm not going to ask you that question tomorrow, though, so don't worry about that. Number 4, which phase of matter does not have a definite shape, yet the particles will not fill the container? So if it doesn't have a definite shape, it means it will take the shape of the container, but it will not take the volume. That would be liquid for number 4. All right, number 5 is a 3-parter. In terms of spacing, what's necessary to change from a solid to a liquid? Well, a liquid has particles that are more spread out, so particles need to spread out. All right, so that's the first part. Second part, what is this process called? So just think of water through its 3 phases. If you have solid water, we would think of that as ice. And going to liquid water, which we think of as liquid water, what is that called when ice turns into water? Melting. What is needed for this process? Got to add heat, right? You just put more space for the first part of number 5? That's fine. Okay, and I'm going to change this background. It's kind of hard to see. All right. Number 6. In terms of spacing, what do you need to do? Go to liquid to gas, same thing. More space between particles. Whatever, something like that. Particles spread out, whatever. And what is this process called? It could be actually 2 here. So if water turns into water vapor, what do we call that? Vaporization or evaporation. If all the particles are turning into gas, you could even call it boiling. Okay, but if it's just some of them. And so what's needed for this process? Again, we got to add heat. Number 7. In terms of spacing, what do we got to do? Go from liquid to solid. We need less space between particles. And so what we're kind of seeing here is this relationship between temperature and spacing, along with the phases and phase changes. Okay, so we should know that if we're adding heat, the particles are going to spread out more, right? So the second part of number 7, what is this process called? When we go from a liquid to a solid, water to ice, we call that freezing. Let's just go with freezing. And so in this case, in order to go this way, we got to remove heat. So again, if we remove heat, less space between particles. Okay, we're making the particles come closer together. This goes along with what we talked about with the thermometer in terms of thermal expansion and contraction, which I will talk more about when we do the thermometer part. All right, number 8, what causes a gas to exert pressure when confined in a container? So the answer to that is gas particles collide, bounce off, with the walls of the container. Okay, so every time those gas particles are bouncing off the walls of the container, that's what's making the pressure. Number 9, how does the total volume of gas particles compare to the volume of the space between gas particles? If you look up at number 2, there's the answer. So number 2, sorry, in the postulates of the kinetic molecular theory, number 2 says these particles are so small compared with the distance between them that the volume of the individual particles can be assumed to be 0. Okay? So the particles themselves we just think of as 0 volume compared with the distance. All right, number 10. As the temperature of a gas decreases, what change occurs in the amount of kinetic energy? So what you got to understand for number 10 is that kinetic energy, this is the main idea here. Start. Kinetic energy is like the speed of the particles. Okay? And that's also related to the temperature. So those three things go together. So if we have a higher kinetic energy, then that means that the speed is higher, so they're moving faster. And if we were to measure that with a thermometer, we would see that we have an increased temperature. And just to tie in the fourth thing that we already talked about, this also means increased space between particles. That's a huge understanding of kinetic molecular theory right there. If you know that one set of relationships, right there, you're good to go. And so vice versa. If we have lower kinetic energy, it means the speed of the particles is lower, which means the temperature is going to be lower, and that also goes along with less space between particles. Okay? So to answer number 10, if the temperature of the gas decreases, the amount of kinetic energy also decreases. Particles will move slower. All right, number 11, what property of gas particles is measured by temperature? Really what we're measuring there is the speed or kinetic energy. And the thing is, since all gas particles, every individual gas particle is not going to have the exact same speed, the exact same kinetic energy, they actually say temperature is a measure of the average kinetic energy. Number 12, what is the relationship between temperature and particle motion? So again, 12, if we have increased temperature, we're going to have increased particle motion. Number 13, in terms of the kinetic molecular theory of gases, explain how increasing the temperature of a gas confined in a rigid container causes an increase in the pressure of the gas. Okay, so if the pressure is because of the particles hitting off the sides of the container, doesn't it make sense that if we increase the temperature, we are going to increase how often the particles collide with the walls? And not only that, but the particles will also be hitting with more force because they're moving faster. Okay? So if you have increased temperature, the particles will move faster, which means they're going to collide with the walls of the container more often and with more force. That means higher pressure. All right, applications. There is a government warning on all aerosol cans that states do not store at a temperature above 120 Fahrenheit. Explain why this warning is required in terms of the relationship between temperature and pressure and the kinetic molecular theory. What do you guys think for that, 14A? What are they afraid happening if the temperature goes up? Okay. It could explode. All the reasons that we just explained up here, increased temperature is going to lead to increased pressure. All right. That's 14A. And 14B, what could happen if an aerosol can was heated above 120? Again, same thing, really. It could explode. 15, what would happen to a completely inflated balloon if it were taken from inside a house to the outdoors in the middle of January in Minnesota? Explain this in terms of KMT. So basically, they're saying you're taking a balloon from a warm environment to a cold environment. So if it becomes cooler, what's going to happen to the speed of the particles? Okay, so the speed is going to decrease. What else is going to happen to the particles? Right, so decreased space means decreased speed means decreased space between particles. This leads to contraction, which means the balloon will get smaller. And that's because it's something called a flexible container. We'll talk more about that tomorrow. But flexible container, so it will actually be able to get smaller. Otherwise, it would just have less pressure. Okay, so that's the whole worksheet. Understand those main ideas I talked about. And then also be able to do the thermometer model. Okay? So let's try to make sure that we hit all our norms here. I want you to be able to model a hot and cold thermometer. And that's what I would just title it, hot, cold thermometer, because we got to have a title. And along with that, I'm going to make one of these have a lower level. Maybe I'll make it red here. And one of them have a higher level. So this would be labeling this. We've got to label it. Cold thermometer, 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 thermometer. And hot thermometer. Okay, so we always got to include particles, right? And I want to make sure that I include the same number of particles in each thing because of the conservation of mass, right? So I'm just going to use 4 particles just to make it easy. So fill the available space, 2, 3, 4, something like that. And I'm also going to have 4 dots here in this one. But as we can see, there's going to be more space now. All right. So we show the particles, we show conservation of mass, having the same number of particles. We should make a key for that. I don't really care if you have mercury particles, alcohol particles, liquid particles. If it's one thing, I don't even care if you just put particles. Okay, but we should have a key of some sort. Okay, maybe alcohol. That's why I made it red. Okay, we also got to show motion. We have to show motion now, right? Okay, so motion. These are liquids, so they are going to be moving around, so I am going to use arrows. Remember with solids, we just use those quotation mark things. But with it being colder, I'm going to make smaller arrows and just pointing in random directions. Cool. And if it's hot, that means they're moving faster, which we show by making longer arrows. Am I missing anything on here? Explanation. So last time I noticed in your models you didn't include words to tell me what's going on. This is a good picture, but explain it to me. Okay? Cold thermometer. Particles moving slower. We now know that that means less energy, which makes sense. Because the particles are closer together also, which is causing the liquid to contract, get smaller. Whereas over here, particles moving faster, more space between them, which causes expansion. And this is moving faster because more energy, so they're getting more energy from their environment. Anything else I'm missing on that? That would be your full points for that modeling, I believe. Nothing I can think of. Any questions about that at all?